Hello everyone. In this video, we continue our discussion of the succeeding cases for the hypothesis test for the two population needs. So for this case, we will discuss the third case, which involves independent samples using the separate variance t-test. So again, to recall, samples are said to be independent of each other if the data obtained from one sample is independent of the data obtained from the other sample and vice versa. So for instance, if we are comparing the average grade of students from traditional classes and the average grade of the students from online methods, then the samples or the grades that we get from the traditional classes do not affect the grades of the students under the online methods. So in this case, we say that the data obtained from the two samples are independent of each other. Now, the third case involves unknown population standard deviations from the first and the second groups, but these standard deviations, even if they are unknown, they are assumed to be unequal. So to explain this better, we have a population. The first population has a data that follows from normal populations. So that means it is represented by the normal curve. And in the second population group, the samples taken are also coming from a normal distribution. However, the width of this normal curve could be different from the width of the normal curve from the first population. So that indicates that the standard deviations of the first population and the second population groups are unequal. Now also, we take note that the samples obtained from the populations are independent from each other and that the sample sizes taken from the two populations are both less than 30. So for case 3, we make use of the separate variance t-test, so it will involve the t-distribution again. Now the formula for the t-test statistic for case number 3 is as follows. It's the difference between the sample means of the first and the second group minus the hypothesized difference d sub 0 divided by the sample standard deviation of the first group squared divided by the sample size of the first sample group plus the standard deviation of the second sample group squared divided by the sample size of the second sample group. Now, since this involves the t-distribution, we have to determine also the degrees of freedom, df or v, in the next slide. So this is the formula for the degrees of freedom, which is rounded down to the nearest integer. So as you can see, the formula for the degrees of freedom is not that simple. So we shall use pH stat only to illustrate this particular case. So to give us an illustration, let us consider this example. The teacher claims that the mean final examination scores of two big sections of advanced calculus are different. The following are the data obtained from samples of 10 students from each section. So this is the data coming from the students in section A, and this is the data coming from the students in section B. At the 0.01 level of significance, is there sufficient evidence to say that the teacher's claim is true? Assume that the distribution of final exam scores is approximately normal with unequal variances. So let's analyze first why this example falls under case 3 or the separate variance t-test. So since we have two populations, so our two populations would be the students from section A and the students from section B. So what we are comparing here is we're comparing the average grade in advanced calculus of students from section A and the advanced calculus grades of the students in section B. Now, according to the assumption, the final exam scores of the students from section A and section B are approximately normal. So, which means that this is represented by a bell-shaped curve, and this is also represented by a bell-shaped curve. Now, notice that I've drawn two bell-shaped curves with different widths. So, as you can see, the width of section B is um, lower or narrower than the width of section A. So that indicates that the population standard deviations of these two populations are not equal, or the population variances of the two populations are unequal. And they are unknown because we don't have any information about the population variances and the population standard deviations. But since we're given with the raw data, we can actually compute for the sample standard deviations of the first and the second group. Now, since I mentioned earlier that we're going to use PHStat, we shall compute these standard deviations using the PHStat software. Now, going back to our hypothesis test, the claim of the teacher is that the average of these final exam scores are different. So that means that the mean for the first group is not equal to the mean of the second group. And since this uses the not equal symbol, we shall put this in the alternative hypothesis, which is our claim. And then for our null hypothesis, it's the complement of the alternative hypothesis, which is mu sub 1 is equal to mu sub 2. So from this hypothesis, we can tell that the type of test is a two-tailed test. So in the next slide, now we see the null and alternative hypothesis. Now, since this is a two-tailed test, we draw the t-distribution curve centered at 0. And since this is a two-tailed test, we will shade both the leftmost and the rightmost part of this distribution. Now, the areas of these rejection regions will be half of the given level of significance. Since our level of significance is 0.01, we shall divide that into 2, and that gives us 0.005 and 0.005 in both sides of this t-distribution. But as I have mentioned, our critical values here in this graph will be computed from our PHStat output. So going back, I'm showing you now the Excel file. So I've encoded the data from both sections A and B. So since this is under case number 3, we will again pick add-ins PHStat, but this time we will pick two sample tests and summarize data. And since we already know that this problem falls under case D, we shall click or tick separate variance test. Okay, so for our hypothesized difference, we shall use 0 because in our null and alternative hypothesis, if we transpose mu sub 2 to the other side, that gives us mu sub 1 minus mu sub 2 equals 0. And that indicates that our hypothesized difference is 0. Our level of significance is 0.01. So we shall change this 0.05 to 0.01. And then we shall encode the data. So for the population 1 sample cell range, okay, we click this part and then we hover our cursor into our data. So we can click this cell involving the label and then drag it up to the last data for section A. And then for the population 2 sample cell range, we do the same thing. and then we click section B and then drag until the last date. Now observe that when we hovered our cursor, we click the cells involving the labels. So we shall check this part wherein the first cells in both ranges contain label. Now, according to our step 1 in hypothesis testing earlier, our test is a two-tailed test. So we have to click two-tailed test and then we click OK. So this is our output. So in the PowerPoint presentation, okay, we have this output. So as you can see that there are two critical values, one lower and one upper, and that corresponds to negative 2.8982 and positive 2.8982. So that means that our lower critical value and the upper critical values are placed in the following locations. So our critical region involves two sides, one at the leftmost and one at the rightmost part of the T distribution. So this shaded region indicates that we have to reject the null hypothesis if the t-test statistic is less than negative 2.8982 or when the t-test statistic is higher than 2.8982. Now for our pH output, we see that the t-test statistic is negative 0.8015, which is located somewhere to the left of 0 and to the right of negative 2.8982. So this indicates that our test statistic is outside of the two rejection regions. So which indicates that our decision is do not reject the null hypothesis. Now going back to our step 1, since we don't reject the null hypothesis, we put a check mark on it. And since the check mark and the claim are located in different hypotheses, that means that there is no sufficient evidence that this claim is correct. So we don't have any evidence to say that the average final exam scores of the two sections are different. So that's what's written in our conclusion. At alpha equals 0.05, there is no sufficient evidence that the mean final exam scores of the two sections are different. Okay, now recall that in case 2 and in case 3, that the population standard deviations are unknown, but in case 2, they are assumed to be equal, and in case 3, they are assumed to be unequal. Now also, cases 2 and 3 involves that the sample sizes are both less than 30. Now, what if we don't have any information about the equality or the inequality of these population standard deviations? So suppose that we only know that sigma 1 and sigma 2 are unknown and the sample size are both less than 30. So in order to identify if the case would be pooled variance t-test or a separate variance t-test, we shall do an additional test to identify the correct case. So that case or that test is called the F-test for the ratio of population variances, or we call it the test for equality of variances. So this test is used if we assume that the average of the two populations, so that's mu sub 1 and mu sub 2, are being compared. And the data coming from both the populations are normally distributed. However, there's no information whether the variances or the standard deviations of the two populations are equal or not. And then, of course, we suppose that the sample sizes are both less than 30. So the F-test is used to determine if the problem will fall under the pooled variance t-test or the separate variance t-test. So to illustrate this, let us use again our problem in example 13.3. Okay, but this time, what we want to know is we need to test whether the two population variances are equal or not. So a teacher claims that the average final exam scores of the two big sections of advanced calculus are different. The following are the data obtained from samples of 10 students from each section. At the 0.02 level of significance, test whether the two population variances are equal. So for the F test, this is how we write the null and alternative hypothesis. So our HO is that the population variance of the first population is equal to the population variance of the second population. And then our alternative hypothesis would be the population variance of the first population is not equal to the population variance of the second population. So this is a two-tailed test. So to illustrate this in the PHStat software or in Excel, we again go back to our data earlier. So this time, we're going to use PHStat, two sample tests, and summarize data, but we're going to pick the F test for differences in two variances. So since the level of significance in the problem is 0.02, we shall change this 0.05 to 0.02. And then we click population 1 sample cell range, and then hover our cursor to our first data, going to the last, and then release. And then for the population 2 sample cell range, we hover our data to the first value from section B up to the last value. Now observe that I did not include the labels when I click and drag the sample cell range. So we should uncheck the first cells in both ranges contain label. Now, since this F test involves two-tail tests, then we have to click two-tail test and then click OK. So as you can see here, the output gives us the upper critical value and the F test statistic. So this means that we need to reject the null hypothesis if the F test statistic is greater than the upper critical value of 5.3511. Now, this F test statistic is actually obtained by getting the quotient between the sample standard deviation squared of the first group over the sample standard deviation squared of the second group. Now notice that this is positive and this is also positive. So this quotient is greater than 0. So which means that it's enough that we get only the upper critical value. So again, the critical region for this F test is to reject the null hypothesis if F is higher than 5.3511. However, the F test statistic that we got here is 1.5387, which is not greater than 5.3511. So which means that our conclusion here is, or decision here is, do not reject the null hypothesis. So which means that if we don't reject the null hypothesis, that means our conclusion is that the population variances of the two populations are equal. So if they are equal, then we use case 2 if we are comparing the means or the averages of the two populations. But if our conclusion is unequal, then we have to use case number 3 or the separate variance test. So this ends the video about case 3 or the separate variance t test and the F test for the ratio of two population variances. Thank you for listening.